Okay, can you see? Yeah. So, hello, my name is Martynas, and today I would like to give a talk about WeaveNet and how WeaveNet uses the vSwitch technology. And basically, WeaveNet is a software for building overlay networks for containers. Our primary target was Docker, but nowadays we started to support Kubernetes, Mesos, and other container orchestrators. So talking about myself, I work as a software engineer at Weaveworks. I believe that this company might be not known to you. It's not Oracle, not VMware. So short introduction. So Weaveworks basically a small company which builds products for managing networking and monitoring containers and microservices in a reliable way and in simple way. And one cool thing about this company that majority of stuff what we do is open sourced. So feel free to check our GitHub repo. You're gonna find quite a lot of interesting projects. So let's start with the problem statement and relevant background information for this talk. So first of all, containers. I believe that most of you are familiar with this concept, but just to recap, for this presentation, you can think of containers as an instance of Linux network namespace. And basically, those are used to isolate global resources, which are associated with network. For instance, network devices, routing tables, firewall rules, and et cetera, et cetera. And in the Linux kernel, network namespace is represented basically by the net struct. And one interesting field in that struct is reference to a user namespace. So basically, it implies that the network namespace can be owned just by a single user namespace. And the other interesting thing is that network devices can belong only to one network namespace, and same applies to a socket. So you might wonder, how can you, having those constraints in mind, how can you communicate between different containers? So in Linux, the standard way is to create the L2 Ethernet bridge and to use virtual Ethernet pairs. So what we do is basically we attach one end of virtual Ethernet pair to the bridge, and the other end we move to the container's namespace, network namespace. So basically, by having this, we can make the communication happen in the case of a single host. But the situation becomes much more interesting once we have multiple hosts involved. So in this case, we have host 1 and host 2. And basically, let's say that container C1 wants to talk to a container C4. So if we run everything on Docker, we can use Docker's port mapping feature, which basically exposes containers port on a host it runs. And in this case, if C1 is a HTTP client and C4 is a HTTP server, so we can basically access the container C4 from C1 by using the public IP address of the host 2 public interface. But what happens if we start a web server on C5? And in this case, we need to we cannot use the port 8 because it's already allocated, so we need to use another port. And basically, this approach brings a complexity to all the configuration management because we need to know about port mappings, not only about IP addresses, but also about port mappings. And instead, we would like to make each container IP addressable. So it means that we want to try to instead of doing this port mapping, we want to directly access a container. And one way to achieve that is to build an overlay network. And so basically, it would mean that we want to decouple the containers network from the physical network. And one way to achieve this is basically what was done in the first iteration of WeaveNet was basically that on each host, we were running a special purpose process, which was installing a PCAP handle on each bridge, and basically it was capturing the packets. So this approach is kind of has quite a huge penalty in performance because we might copy a packet twice. Also, we do unnecessary context switching between user and kernel space and vice versa. And also, we waste CPU cycles instead of doing useful work. So basically, that brings us to our motivation or to a problem statement that what we want to do with the Open vSwitch, we want to build a fast multi-host overlay networks for containers. And yes, when I say fast, I do not mean really fast. I do not mean any like kernel bypassing. I just mean faster than PCAP implementation, let's say 4 times faster than PCAP. And we do not target like really large so-called Google scale deployments. Okay, so let's move to our approach. So to address the PCAP issues, we decided to use the Open vSwitch technology, and in particular, we decided to use in-kernel component of the Open vSwitch. So basically, how we start, we create a special control plane process written in Go. So it's like a small application, small process running on your host. And that process creates a data path, the Open vSwitch data path on a host it runs. And then what it does, it attaches all containers to vPorts, which we create before. And basically, by having this, we have kind of similar setup to the one that we have with the L2 bridging. And this setup doesn't work because the in-kernel component of Open vSwitch doesn't have L2 bridging capabilities. So what we need to do, we need to create a mesh handler, like install the mesh handler. And this mesh handler, which you can see on the screen, is basically resembles the functionality of L2 bridge. So it learns about source MAC addresses of the packets it sniffs. And if it already knows the destination of the packet, it basically sends that packet to a vPort. And if it doesn't, it basically broadcasts the information. It broadcasts the packet it has received. And basically, send and broadcast operations results in installation of the flow. So in this case, we create a simple flow which basically says that, okay, so if the container 1 sends something to container 2, so and it originated from the vPort 1, so then please send to the vPort 2. And next time you're going to send a packet, no mishandling will occur. So far, so good. And the situation becomes again, much more interesting when we have multiple hosts. So for that, we use VXLAN tunneling, and we use that in quite a primitive way. We use that just for encapsulation and for sending and receiving packets. And basically, a nice thing about VXLAN that in its header, it contains 24-bit segment, which we can use for identifying sending and receiving host. And it's needed for us because it's quite essential for us because as you're going to see later, we do multi-host overlay routing. So we need to know what's the ID of the destination host. And in the case of VXLAN vPort, we need to change a bit our mesh handler. So in this case, as you can see, the first line, basically what it does, it extracts the host ID, like source host ID and destination host ID. And if the packet's destination is to us, then we basically, if the packet is destinated not to us, then we basically relay the packet. Or if it's destinated to us, we inject the packet into the data path, and otherwise we just do the broadcast. And in one of these cases, we installed the flow, and basically the flow, this flow is a bit much more interesting because it contains tunneling information, but it's relatively simple. So when I mentioned in the beginning that we rely just on the in-kernel components, that means that we do not interact with user space daemons which come with the vSwitch distribution. So instead, we wrote our own library, which is written in Go, and this code snippet shows you, it's a bit ugly, but it shows you how you can interact with the data path interface. And basically, it uses the netlink interface, and it's relatively simple. And again, it is open source, so feel free to use it in your projects. And yeah, one missing piece in all this big picture is basically how do we propagate routing and reachability information, also like known as topology information. So one common approach in containers networking is to have a distributed consistent data store such as console or etcd, but we think that this approach brings a necessary additional complexity because some people, like operation people, need to manage such data stores. And also, etcd and console are based on Raft algorithm. And if the majority of master nodes are down, so then basically your database is not functioning. So instead, we take a bit different approach. So we use again, our in-house library, we call it Mesh. So this library is a gossiping library. And what it does, in each Weave router, which you saw before, we do the gossiping. And once we learn something new about the topology, we basically broadcast this information to our neighboring peers. And also, we do this broadcasting periodically. So in terms of CAP theorem, we have availability and partition tolerance, but we sacrifice consistency. So that means that we need to handle merge conflicts. And to address merge conflicts, we are using CRDTs. So it's like a special data types. And this topic is kind of really theoretical and also can be also practical. And I'm not going to dive into details. And if you're willing to learn more about it, I recommend you to watch a brilliant presentation by my coworkers, which was, I think, was presented last year at KubeCon in London. So yeah. Again, this library is open sourced, and you can use for your own projects. You can build a peer-to-peer networks. You can build DNS servers, as we did with this library. So the other features of WeaveNet, which I didn't mention, is basically that we integrate with Docker, and there are multiple ways how we can do that. So one is we integrate via Docker plugins. It's quite standard way. Also, we wrote a Docker proxy, so it's like a man-in-the-middle proxy, which sniffs the communication between a Docker client and Docker daemon, and we basically inject the necessary information into packets and and based on that, we do some changes in Weave router. And also, we support CNI plugins, so basically, we can do networking for Kubernetes and Mesos. The other features of WeaveNet is that, as I mentioned before, this gossip library is really generic. So on top of that library, we built our DNS server, which doesn't rely on any consistent store. So basically, all the DNS entries are broadcasted in the network. And the same we did with the IP address management. So all the IP allocations are broadcasted in the gossip cluster. Besides that, we support encryption, but overlay encryption, but it only exists in the PCAP version, which still is in use by someone. And we are currently working on vSwitch encryption, so which will going to be based on IPsec. And next, we support multicasting networks, which do not support multicast because we do L2 networking. Okay, so the integration is relatively simple. If you look at the lines of code for the fast data path, it's like 1,000 lines of code, not considering the netlink library which we wrote. And it was but we have encountered two major problems with the Open vSwitch integration. So one was that missing contract support. And this is quite essential because one product which is used for monitoring containers, it relies a lot on contract information. So some links, like some connections, if they were happening over data path tunnels, they were not shown in Weave scope. And basically, this forced us to change a bit the design which I presented before. We had to introduce intermediary bridge, which is to which we, like L2 Linux bridge, to which we connect each container. And basically, then we connect that bridge with the virtual Ethernet pair. It's a bit ugly, and we also had to sacrifice the performance a bit. And but basically, this contract support is, I believe, is fixed in 4.2 kernel version. But the problem is that we have to support quite old kernel versions. So in the future, we might implement a knob or some similar approach. And the next problem was that we create VXLAN vPorts by using Open vSwitch. So basically, we don't have any underlying device, net device for VXLAN we create. And the thing with this is that I believe after some refactoring, code refactoring, such VXLAN devices had a strict limitation of MTU. It was like you cannot create a VXLAN device with larger than 1,400 MTU value, but it got fixed in 4.5. So basically, it means that with older versions, if you didn't backport a patch, you couldn't take advantage of jumbo frames, which is quite present in the existing cloud environments. And yeah, so finally, evaluation. So as I said, we wanted to be a bit faster than the PCAP implementation. And we did not so scientific benchmarking, I would say, with WeaveNet on Amazon's AWS EC2. And we used 2 instances, and we ran iPerf test. And basically, each instance was running Ubuntu, the latest LTS distribution, and which is based on the 4.4 kernel version. And basically, the results for throughput are the following. So as you can see, the native host throughput, I forgot to mention that the link between hosts was 10 gigabits. So as you can see, the throughput is of the host is really close to those 10 gigabits. And with the FastDP, if we use a large MTUs, so like close to 9,000, we couldn't use 9,000 because we need to take into consideration VXLAN overhead, which is like 50 bytes. So what we do, we get a really close performance, which is nice in our case. And FastDP with the default MTU, which is 1,410, the performance is still better than sleeve performance. And I forgot to mention that sleeve, that's how we call it PCAP overlay implementation. So I believe that I have a bit of time for demo. So let's try to run the demo. And before, I will just show you my setup. So I'm gonna have like on Vagrant 3 hosts, and I will black hole the packets between host 1 to host 3 by basically installing IP tables rule. And between host 1 and host 2, I will create a fast data path tunnel, and between host 2 and host 3, I will use the PCAP-based implementation. And what I'm gonna do, I will run a container C1 on host 1 and container C3 on host 3, and basically I'll try to send the dummy packets between them. Okay, so it's a bit, okay, let me try to move. Yeah, so there we go. So I have host 1, host 2, and I'm skipping the installation step of WeaveNet, but it's really simple because WeaveNet runs in a Docker container, and basically it's one line to get Weave running on your host. So let me check. So I have just Weave Scope running, so Weave Scope probe running, which I'm using for monitoring. If I'm gonna have time, I will show it, but let's concentrate on WeaveNet first. So, okay, so I'm gonna start Weave launch. So I'm gonna start Weave on the host 1, and let's see, okay, so I can ping, and yeah, let's install a rule for dropping packets. So, okay, so host 3, okay, no packets can flow. Next, I'm gonna launch Weave on host 2. And because we are using gossiping, you don't need to specify all peers to which you want to connect, because the gossiping library allows WeaveNet router to learn about the topology. And so, but in this case, I need to specify because it's the second peer. So I'm from the host 2, I'm connecting to the Weave router, which runs on host 1. So yeah, and if I run Weave state, connection, I'm nervous, so I'm mistyping. So you can see that there's an established FastDP connection, so the one that is based on Open vSwitch. And from here, I will try to, okay, I said that I want to disable fast data. So I'm gonna run the sleeve overlay, and I will connect to host 2 because I'm not able to connect to host 1. And let's see what we have. Connections. Okay, so we see that it has established connection to host 2, but it's not able to establish. It tries to connect to host 1, but will be not able. So now I'm gonna start a container, and I will start container by using Weave proxy. So basically, I just add some variables to a regular Docker client command line tool, and I will start a simple container, and I will attach to that container. So and the same I'm gonna do with the container on host 3. Okay, so yeah, name c3td alpha and bnsh. Okay, and now I should be able to ping the container. So yeah, let's ping the container C1. Oops, something is wrong. Ouch. I shouldn't do. 1 second. So, yeah, sorry. Good spot, thank you. So, status, connections, Docker exec. Yeah, so I'm able to ping. And if I dump the flows installed on this container, on this host 1, you will see that there's a flow which says to send the traffic from, to send the packets from host 1 to host 2, not to host 3, because there's no direct link between host 1 and host 3. And let me try to find that rule just to show you that it actually works. Yeah, so it should be, yeah, so basically it should be this for traffic originating from host 1 to host 3, please send it over VXLAN tunnel, which is established between host 1 and host 2. Yeah, so more or less that's it what I wanted to show you. And if you have any questions, feel free to ask me. And yeah, just want to say that for all this work, I should mention credits, give credits to WeaveNet team. and in particular to Matthias, Brian, Adam, and David Bragg, who left Weaveworks. So he used to work a lot on this. Yeah, so that was it. Questions, welcome. Thank you.
Yeah, you said you don't scale to Google-size scales. What do you scale?
I would say like up to 100 hosts, you should be fine. We haven't done any serious benchmarking with thousands of hosts. We are planning that to do, but.
Do you have reason to believe that it wouldn't scale to thousands of hosts?
I believe that gossiping might be a bottleneck for that.
Is there a foundation for using systems other than the gossip protocol to distribute the state necessary to coordinate?
In Weave, we just do gossiping. But I know that some other container networking solutions, they do BGP, they run BGP, but they do L3 networking. So we do L2, so that's the difference.
We have time for one or two more questions.
Let's thank our speaker.
Thank you.